mid-February 1943, Sidi Bou Zid, Tunisia. The captured M4A1 Sherman tank ground to a halt in the desert sand, its American star still faintly visible beneath the hastily painted German cross. Officers from the Heavy Panzer Battalion 501 quickly gathered around their prize, notebooks in hand. This single, fully operational American tank, taken intact during the Battle of Sidboid, would spark a crisis of confidence among German engineers, even above the repertoire, one of which would reverberate through their tank development programs for the remainder of the war. The battlefield math of armored warfare was about to be rewritten, not through thicker armor or heavier firepower, but through a quality the Germans had long overlooked: sheer mechanical reliability. The tank, christened War Daddy II, carried the serial number USA 36741 and had been built by Lima Locomotive Works for Company G of the 1st Armored Regiment, 1st Armored Division. German reconnaissance personnel drove this Sherman 350 kilometers across North African terrain to the port of Sfax. A grueling 4.5-day journey. Every kilometer, challenged long, held German assumptions about American industrial capability. The engine never overheated. The transmission never faltered. The final drives performed consistently. German crews, accustomed to frequent mechanical breakdowns even on short maneuvers, watched uneasily as this enemy machine soldiered on, uncomplaining, through terrain that would have immobilized their own tanks. At Sfax, War Daddy II was loaded onto a cargo ship bound for Germany under strict orders from the Army Weapons Office. It must arrive at the testing facility in Kummersdorf intact and fully operational. Until now, German intelligence had only fragmentary reports on American tank production. But seeing the vehicle firsthand turned numbers on a page into undeniable reality. The Sherman embodied mass production at a scale Germany could not replicate. Using automotive engineering principles their industry had yet to master. As the ship steamed across the Mediterranean, Wehrmacht engineers prepared detailed testing protocols, bracing to confront uncomfortable truths about their own limitations and the surprising sophistication of American designs. Spring 1943, Kummersdorf Proving Ground, Brandenburg, Germany. War Daddy II rolled off the transport rail car, now labelled Zugfahrts 259 and sporting German license plate WHO5A941. Engineers had already stenciled armour thickness and angles across every surface, preparing for a comprehensive evaluation. Kummersdorf, located 25 kilometers south of Berlin, served as the German Army's central testing ground for both domestic and captured Allied vehicles. Here, meticulous engineers measured, tested, and analyzed everything from track tension to transmission efficiency, recording every observation in exhaustive technical reports. The Sherman was about to face the most thorough automotive scrutiny German engineering could devise. Specialist teams from multiple technical branches conducted the initial inspection. Every component was photographed from dozens of angles, every clearance measured with precision instruments, and construction methods documented. often appearing astonishingly simple compared to German standards. The transmission immediately drew attention. Where German tanks relied on straight, cut gears requiring exact tolerances and frequent maintenance, the Sherman employed herringbone gears, spreading stress across multiple teeth simultaneously, a hallmark of American automotive engineering since the 1930s. This design offered exceptional durability with minimal precision. German engineers had long considered herringbone gears too difficult to mass produce. Yet the Americans manufactured them by the thousands. Testing began with controlled automotive trials designed to push every system to its limits. Engineers drove the Sherman through obstacle courses, simulating battlefield conditions, recording fuel consumption, engine temperatures, and transmission performance across varied terrain. After each trial, components were disassembled to inspect wear patterns and detect potential design weaknesses. The results defied conventional German assumptions about the trade-offs between performance and reliability. In every category, the Sherman performed admirably, and in the one metric where German tanks consistently failed, it excelled operational endurance without maintenance intervention. The powertrain revealed stark differences in design philosophy. The Sherman's transmission featured 5 of forward gears plus 1 reverse, with synchronization in gears 2 through 5, eliminating the need for double clutching. This made it almost as easy to drive as a civilian car, requiring minimal training. German crews, in contrast, spent hours mastering complex clutch techniques and precise throttle control to avoid transmission damage. The Sherman assumed that ordinary soldiers with basic automotive knowledge would operate it, while German designs depended on highly trained specialists. The Continental R9775 radial engine in this Sherman proved remarkably resilient. It maintained consistent performance across extreme temperatures where German engines would overheat or lose power. Its simple but effective cooling system and air filtration handled desert sand without clogging, highlighting a design philosophy prioritizing practical reliability over theoretical optimization. June 6–7, 1943. Hillis Lean Artillery Range. Reich Minister Albert Speer presided over a major armaments conference attended by industry leaders and senior Wehrmacht officers. The demonstration included hill climbing trials comparing German tanks with captured Allied vehicles. War Daddy 2 sat alongside the latest German models, including the Panther D, fresh from production, and the Ferdinand tank destroyer, representing the pinnacle of German armored technology. Speer, responsible for armament production and personally accountable to Hitler, sought to understand American industrial capabilities and see how German designs measured up. The demonstration delivered uncomfortable truths. The Sherman ascended the test slope effortlessly. Its synchronized 5-speed manual transmission shifted smoothly, and its engine maintained steady power. The driver exhibited confidence and ease of operation, a hallmark that would define the Sherman. The Panther powered by its 700 horsepower Maybach H-Elv 230 engine, matched the Sherman's climb, but only with great effort. The 65-ton Ferdinand, despite its advanced electric transmission, stalled halfway up, requiring recovery crews to intervene. Years later, in his memoirs, Speer would reflect on the Sherman's remarkable mobility. During his inspection tour of Italy in October 1944, reports had praised its cross-country capabilities. Noting its ability to climb mountains, German experts had long deemed impassable to tanks. He attributed this superiority to the Sherman's powerful engine relative to its weight, granting it cross-country mobility on flat terrain that clearly exceeded that of German tanks. The 26th Panzer Division had specifically reported this advantage. Observations from Germany's armaments. Minister carried considerable weight within Wehrmacht circles. A public assessment appeared in Das Reich newspaper on June 27, 1943, describing the Sherman as a remarkable achievement from North American laboratories and praising it as an exceptional product of the continent's steel industry. From above, the article highlighted the tank's serial construction and adherence to the almost audacious standards of the North American automotive sector. It also noted the gyro-stabilized gun, the first attempt of its kind anywhere, underscoring American ingenuity. While the public statements were carefully worded for propaganda purposes and avoided appearing defeatist, they concealed the growing private alarm within German engineering departments. American tanks were not just adequate. They were fundamentally better designed for sustained operations in the field. Back at Kummersdorf, systematic testing continued through the summer and into autumn of 1943. Engineers measured the Sherman's operational range through extended trials, documenting distances exceeding 2,000 kilometers before major maintenance was required. Roughly 4 times the range early model Panthers could manage in real-world conditions. Transmission efficiency surpassed any German tank, with power losses through the drivetrain significantly lower than comparable German systems. The Sherman's synchronized manual transmission allowed smooth gear changes without double clutching or careful rev matching. Unlike German tanks, its final drives also challenged German assumptions. Panthers used systems inherited from the Tiger design, prone to failure under stress. Straight-cut gears in inadequate housings meant Panther final drives often broke after relatively short distances, sometimes less than 100 kilometers. Sherman final drives, built on the same herringbone gear principles as its transmission, rarely failed, even in sustained combat conditions. Restoration projects, decades later, found Shermans that needed virtually no mechanical work. After years of storage, a testament to their generous design margins. By late 1943, Kummersdorf had compiled enough data for comprehensive internal reports circulated among Wehrmacht technical branches. These documents painted a sobering picture. The Sherman reflected a level of American automotive engineering Germany lacked. Despite its theoretical knowledge, mass production allowed looser tolerances that that German precision manufacturing might have scorned, yet resulted in far more reliable vehicles. Interchangeable parts enabled field repairs with basic tools and minimal training, while German tanks often required specialized equipment and factory-level precision. American industrial advantages extended beyond production numbers. Decades of civilian automotive experience informed tank design. Before the war, cars were commonplace across the US, while in Germany, automobiles remained luxuries for the wealthy and party elite. The Volkswagen program, initiated in 1934, delivered fewer than 1,000 civilian vehicles by 1939. This difference in automotive maturity directly influenced tank design philosophy. American tanks could be maintained by mechanics with civilian automotive skills, while German designs demanded specialists and constant expert attention. By late 1943 and early 1944, the reliability gap was undeniable. Panther tanks required strict operational limits to prevent mechanical failures. Drivers were warned against frequent gear changes, especially third gear, prone to breakage, and could not safely perform pivot turns or reverse maneuvers without risking transmission damage. Foreign debris could jam drive sprockets, immobilizing vehicles for hours. Despite Panthers being produced in dedicated factories using the best German materials and skilled labor. By contrast, Sherman tanks were designed by automotive engineers at General Motors, Ford, and Chrysler, applying decades of mass production experience. Commercial automotive components were widely used, leveraging established supply chains. The transmission, for example, was manufactured by Caterpillar Tractor, BIC, and Ford, all to identical specifications, fully interchangeable without adjustment. Standardization common in American industry remained largely theoretical in German production, where subtle differences between manufacturers often prevented true parts interchangeability. Additional Shermans captured from British units in Italy and Soviet forces on the Eastern Front arrived at Kummersdorf in 1943-44, undergoing the same rigorous testing. British Firefly variants, fitted with 17-pounder anti-tank guns, drew particular attention, demonstrating the Sherman's inherent design flexibility, an upgrade potential Germany's Panthers lacked without complete redesign. Reliability trials simulated combat conditions over hundreds of kilometers. Mechanical incidents, maintenance requirements, and component failures were meticulously recorded. Comparisons with Panthers and Tigers revealed a stark contrast. Operational readiness for Panthers averaged below 40% in 1943, sometimes dropping to 20–25%. Individual battalions reported fewer than 1 in 5 tanks capable of combat. Shermans, by contrast, maintained substantially higher availability across all theaters. Specific German field reports reinforced these findings. During Operation Citadel at Kursk, in July 1943, Panthers achieved only 16% operational readiness. Mechanical failures outnumbered enemy action. Even as incremental design improvements raised readiness to 78% by May 1944, Panther performance never matched Sherman's from initial production. Sherman diesel engines exceeded 3,000 km between overhauls, while Panther engines barely reached 1,000 km. Transmissions and final drives demonstrated similarly superior durability, requiring minimal maintenance compared to German vehicles. Captured Shermans also proved immediately effective in German service. Unlike Soviet T-34s, which required extensive modifications, Shermans needed no alterations. German crews accustomed to frequent breakdowns marveled at the tank's reliability. Reports from panzer regiments noted that Sherman operators could focus on tactics and combat, while Panther and Tiger crews constantly worried about reaching the battlefield intact. The 10th SS Panzer Division, for instance, captured 12 M4A3 Shermans at Hellesheim in January 1945 during Operation Nordwind. Vehicles immediately pressed into service with remarkable effectiveness. These tanks had originally belonged to the American 4th Tank Battalion and were captured intact after their crews abandoned them during the German offensive. The 12 Shermans were reorganized into the 13th Company of the 10th SS Panzer Regiment, serving in combat operations for the remainder of the war. They were deployed as reconnaissance vehicles and mobile reserves, roles demanding extended movement without frequent maintenance and reliable mechanical performance. German commanders had already seen what Kummersdorf testing had proven years earlier. American tanks could be counted on to operate when needed. In the final months of the war, this dependability often outweighed firepower or armor. A Sherman that reached the battlefield, operational, was far more valuable than a Panther with superior firepower stranded 20 kilometers behind the front lines due to mechanical failure. By January 1944, expanded testing programs were underway as Wehrmacht forces retreated across multiple fronts, and additional captured vehicles arrived at Kummersdorf. Engineers examined the M4A1 with its Continental R975 radial engine, recording its performance characteristics and comparing it with other variants. The M4A2, powered by twin General Motors 6046 diesel engines, demonstrated superior fuel efficiency and distinct operational traits. The M4A3, equipped with the Ford GAV8 gasoline engine, was favored by American crews as the best Sherman power plant. Despite differences in engines and configurations, every Sherman variant shared a key trait: outstanding automotive reliability, rooted in solid engineering and consistent manufacturing processes. German engineers were particularly impressed by this consistency, having long been accustomed to significant quality variations between vehicles produced by different factories under nominally identical specifications. The diesel-powered M4A2 stood out even more. Thousands were supplied to the Soviets under Lend-Lease, and many were captured by German forces during retreats on the Eastern Front. Its twin GM6046 diesel engines offered comparable performance to any Sherman variant while consuming far less fuel, a critical advantage as German fuel supplies dwindled. German designers had experimented with diesel engines for tanks but abandoned the effort due to manufacturing complexity and the intricate fuel injection systems required. By contrast, American industry produced diesel Shermans alongside gasoline variants without disrupting production schedules, demonstrating flexibility and technological sophistication that German industry could not match under wartime conditions. In March 1944, reports from General Heinz Guderian, Inspector General of Panzer Troops, claimed that improvements in Panther reliability had reached acceptable standards. Engine lifespans were now 700 to 1,000 kilometers, and final drive failures had been largely addressed through design tweaks and enhanced manufacturing processes. While presented as a major achievement in German military communications, these improvements merely brought the Panther to a level that Shermans had consistently achieved from the beginning of their production in 1942. The contrast highlighted just how far behind German armoured vehicle development had fallen. The gap grew even starker as German tank production increasingly suffered from resource shortages and the effects of Allied strategic bombing. Key factories in the Panther and Tiger production chain were targeted with growing effectiveness. On the night of April 27-28, 1944, the Maybach engine plant in Friedrichshafen was heavily damaged during a raid involving 322 RAF bombers. Archives at the Imperial War Museum describe this as the most destructive raid on German tank production during the entire war. The attack also destroyed the adjacent ZF gearbox factory, halting production of engines and transmissions for 6 months. When production resumed in November 1944, quality control had already deteriorated. Increasing reliance on forced labor. As German workers were conscripted for military service, introduced deliberate sabotage. Cigarette filters were jammed in oil passages, gaskets were installed incorrectly, and components were assembled with improper clearances. None of these issues affected Sherman production. Safely carried out in American factories far from the battlefield, staffed by motivated workers earning fair wages under stable conditions. The fundamental difference between American and German tank production lay not in knowledge, but in industrial capacity and design philosophy. German engineers possessed theoretical expertise comparable to their American counterparts and understood automotive principles, but they rarely applied these consistently to tank design. Instead, German tanks prioritized high-performance specifications that looked impressive on paper, but often failed to deliver reliable operation under combat conditions. In contrast, American tanks emphasized practical, maintainable engineering that ensured vehicles could survive and function in the field. The Panther's powerful 75 Umdendammen KWK-42 gun and thick frontal armor came with a hidden cost, an overstrained powertrain that could not reliably support the tank's 45-ton weight. The Tiger, equally formidable, demanded complex maintenance and frequent repairs by highly trained specialists. These trade-offs might have been acceptable if German industry could produce enough vehicles and spare parts to keep them operational. but it could not, especially as Allied bombing intensified and resource shortages deepened. In contrast, American engineers, steeped in decades of civilian automotive mass production experience, designed tanks that could be manufactured by the tens of thousands and maintained by mechanics, with basic training, relying on skills learned in civilian life. The Sherman's powertrain used components already proven in commercial service, drawing directly from automobile and truck engineering. Its electrical system even included a backup generator capable of powering the turret traverse. If the main engine stalled, a feature German designers once dismissed as a luxury, but which proved invaluable in combat. German tankers could only imagine such conveniences, particularly those who had suffered turret traverse failures when engines stalled on slopes. These features never appeared in German technical specifications because designers prioritized armor thickness and gun power over practical battlefield reliability. By spring 1940, Wehrmacht units across all fronts reported escalating mechanical problems as manufacturing quality deteriorated and spare parts became increasingly scarce. Panthers needed to be transported by rail for movements over 100 kilometers. Since their final drives could not survive sustained road marches, field orders explicitly restricted Panther movement to preserve the vehicles for combat, rather than risking mechanical breakdown during approach marches. Even the Borgwood Panther recovery vehicle, built on a Panther chassis to tow disabled tanks, suffered the same reliability issues as the tanks it was meant to rescue. German commanders faced the stark reality. Mechanical failures eliminated more tanks than enemy fire, with some units reporting that 70% of losses were due to breakdowns rather than combat. Meanwhile, Sherman production surged at rates Germany could never match. American factories produced 49, 324 Shermans over the course of the war, more than all German tanks of every type combined. British Commonwealth forces received thousands through lease. The Soviet Union over 4,000 diesel variants. And Chinese forces in Burma used Shermans to devastating effect against Japanese armor that was technologically inferior to both American and German designs. Every theater confirmed what Kummersdorf testing had revealed. Properly maintained Shermans kept running under conditions that would disable or destroy German tanks. German crews who captured and operated Shermans universally praised their reliability in letters, official reports, and post-war interviews. Eastern Front reports noted that even the complex Chrysler A57 multi-bank engine, with its 5 separate blocks, was easier to troubleshoot than German engines, which demanded specialized knowledge and tools. The Ford GRA V8, lauded by Allied crews for its power and dependability, was remarkably reliable to German mechanics accustomed to Maybach engines requiring constant adjustment of valve clearances, ignition timing, and carburetors. Even the General Motors twin diesel, originally rejected by the US Army for front-line use and relegated to lease, outperformed any German diesel engine in tank service The Sherman's generous design margins offered another crucial advantage. Transmission and final drive components specified for the 30-ton M4 with 400 horsepower required no major modification to handle the 42-ton M4A3E2 Jumbo with its heavier armor. The same components could even transmit 650 horsepower from experimental engines without failure or reinforcement. German engineers often viewed such overbuilding as wasteful, consuming scarce materials without immediate benefit. American engineers understood that these margins provided growth potential for future upgrades and battlefield reliability, making the investment worthwhile over the vehicle's service life. By summer 1944, German tank commanders confronting the Allied invasion of Normandy realized their disadvantages extended far beyond individual vehicle capabilities. American artillery, close air support, and logistical superiority overwhelmed German forces regardless of tank specifications or tactical skill. Yet Sherman reliability meant American armored units could sustain continuous operations that German panzer divisions could not. U.S. tank battalions could launch attacks, maintain combat pressure, conduct pursuits, and immediately prepare for the next mission without long maintenance halts. German units, by contrast, had to ration movements carefully, knowing each kilometer consumed precious component, life and edged vehicles closer to mechanical failure. Operational availability, more than firepower, often determined which side could keep the offensive momentum. The German use of captured Shermans provided final confirmation of American automotive superiority. During the Battle of the Bulge in December 1944, the 150th Panzer Brigade, formed for infiltration operations, sought captured American vehicles to disguise its movements. Shermans were specifically requested for their reputation for reliability. However, the brigade received only 2 Sherman tanks, and just one was serviceable enough for operations, reinforcing the lesson that dependable engineering could decisively influence the battlefield. The serviceable Sherman never actually saw combat. Blocked by massive traffic jams that prevented the infiltration operation from reaching its objectives. In missions demanding vehicles to operate without breakdowns deep behind enemy lines, only American tanks offered any reasonable chance of success. German tanks, even when fully functional, could not provide the sustained performance such operations required. January 23, 1945, marked the final official acknowledgement of German automotive failure. A Panzer Commission meeting produced a report detailing catastrophic final drive failures across all German tank types. The findings were staggering. Prior to the 1945 Eastern Offensive, the Panzer IV had 500 defective final drives, the Panther 370, and roughly 100 in the Tiger. Additionally, about 200 failures were reported in the Hetzer tank destroyer, based on the 38-ton Czech chassis. General Wolfgang Thomel, Chief of Staff under Inspector General Guderian, explained the operational consequences bluntly. Under such conditions, orderly use of tanks was impossible. Crews lost confidence in their vehicles, sometimes abandoning them entirely due to final drive fears, worried they would be stranded and captured. German tanks, designed to awe with impressive specifications, failed in the most fundamental requirement: mechanical reliability sufficient to reach the battlefield and complete missions. By early 1945, Kummersdorf testing facility prepared for evacuation as Soviet forces relentlessly advanced on Berlin. Engineers frantically packed testing data, shipping documentation westward to preserve technical intelligence for post-war analysis. Some captured tanks, including at least 2 Shermans, were pressed into improvised combat service, fighting alongside German designs in the final desperate defenses of Berlin. The Shermans continued to operate until destroyed by enemy fire or abandoned due to fuel shortages. German tanks, including Panthers and the remaining Tigers, frequently broke down at rates that shocked even crews accustomed to poor reliability. The story of War Daddy 2 and the dozens of Shermans tested at Kummersdorf highlights one of World War II's most striking industrial disparities. German engineers, constrained by an industrial system that prioritized theoretical perfection over practical function, produced tanks that looked formidable on paper but failed under prolonged field conditions. American engineers, drawing on decades of civilian automotive manufacturing experience, produced tanks that, while less technically sophisticated in certain areas, operated reliably under conditions that routinely defeated German vehicles. In armored warfare, as in most military operations, the weapon that works, when needed, always outperforms the one that is theoretically superior, but cannot reach the fight or complete its mission. Post-war analyses by American and British intelligence confirmed Kummersdorf's findings. Systematic examination of destroyed German tanks revealed mechanical failures as frequent as combat damage, final drives shattered under stress, transmissions seized from poor lubrication or operator error, and engines destroyed by overheating or oil starvation. Germany's obsession with high performance specifications blinded designers to reliability and maintainability. Their tanks required highly trained specialists to operate and maintain, supported by a logistics network that collapsed under the strain of supplying countless unique components to scattered units. The lessons learned at Kummersdorf had a lasting influence on post-war German tank design. When West Germany developed the Leopard 1 main battle tank in the 1950s, engineers deliberately emphasized reliability and maintainability over raw performance. They studied American automotive engineering principles, applying them to military vehicles. The Leopard 1 incorporated many philosophies that had made the Sherman successful. A robust powertrain with generous design margins, easy maintenance with minimal specialized tools, standardized components for rapid field repair, and built in growth potential for future upgrades without complete redesign. The Leopard 1 went on to become one of the Cold War's most successful tank designs, serving with numerous armies and remaining in production for decades. The captured Shermans at Kummersdorf, including War Daddy 2 with its name, still painted on the hull, represented far more than enemy vehicles brought home for technical study. They were living proof that industrial maturity and practical engineering experience mattered far more than theoretical technical innovation really pursued. Without regard for manufacturing realities, German tank designers had believed that superior technology alone could overcome material shortages and numerical inferiority. But they were wrong. American tank engineers, by contrast, built reliable vehicles because decades of hands-on experience had shown them that logistics, maintenance capability, and sustained operational readiness determined victory in modern mechanized warfare. They were right, and their approach proved decisive. The reliability gap between Shermans and German tanks shaped not only tactical armored warfare, but also the broader understanding of industrial capacity as a decisive factor in modern conflict. Germany entered World War II with technical advantages in many weapons systems, backed by exceptional scientific knowledge and engineering expertise. Yet, it lacked the industrial depth and mass production capability to sustain these advantages while fighting enemies on multiple fronts. The United States, by contrast, produced weapons that were often less technically advanced, but could be manufactured in overwhelming quantities, continuously improved based on combat experience, and supplied to allies through lend-lease, all while maintaining the highest standard of living among combatant nations. Sherman tank design and production perfectly exemplified this approach. The US produced nearly as many Shermans as Germany produced all tanks combined, while simultaneously building vast quantities of other weapon systems. Industrial capacity, more than any single battle, ultimately decided the war. The math was simple and brutally clear. A Sherman, armed with a 75-1 ready gun that reliably reached the battlefield and fought effectively, was far more valuable a Panther with a superior gun that broke down before engaging the enemy, or required 3 days of maintenance for every day of operations. A tank battalion with 80% of its vehicles operational could execute missions that a unit with only 40% operational vehicles could not even attempt. Reliability was not a convenience. It was the foundation of operational effectiveness. Above, German tanks consistently failed this critical test throughout the war. American tanks consistently passed it. By mid-1943, Kummersdorf testing had proven this beyond reasonable doubt. German commanders continued deploying Panthers and Tigers that looked imposing and possessed impressive specifications, yet could not be counted on to function when it mattered most. The Sherman did not win World War II through superior firepower or armor. It won through industrial superiority, expressed as mechanical reliability, consistent availability, and ease of maintenance. By mid-1943, German engineers at Kummersdorf understood this. They produced exhaustive reports, tested their findings rigorously, and reached the correct conclusions about American advantages. But understanding a problem and solving it are different challenges. German industry lacked the capacity to redesign production around reliability principles, while simultaneously waging a losing war on multiple fronts against an enemy with superior resources. American industry, in contrast, had built reliability into its civilian automotive sector over decades and extended those mature principles to military production with remarkable success. War. The single Sherman captured in Tunisia and subjected to months of exhaustive testing at Kummersdorf told the entire story through its flawless mechanical performance. Every kilometer it drove without failure was evidence that German tank design had taken a fundamentally wrong path by prioritizing specifications over reliability. Every test demonstrating American automotive excellence proved that practical industrial experience mattered more than theoretical calculations. Every comparison between Sherman and German tank reliability revealed that Americans had solved problems that German engineers didn't even realize needed solving. The tank itself was, in many ways, unremarkable. Just one of 49,000 produced. What it represented, however, was devastating to German confidence. Proof that Germany had already lost the industrial war, even while fighting continued, and that American productive capacity could not be matched, regardless of German technical sophistication or tactical skill.